Okay, so here we are, we're back, and we're looking at intermolecular forces. All right, so what this is about is us trying to understand, really ultimately, we want to understand why substances have the physical and chemical properties that they do. And again, we look at the properties that we can see with our eyes and measure with our tools. We use those to predict properties of individual molecules. And so the important thing to note here is that when I have, say, a beaker and it is filled with water, I don't just have one water molecule here. I don't have 10 water molecules here. I have billions of billions of billions of water molecules here. So the behavior of the water is not just about what that water molecule looks like, which now you and I know it's a lovely little bent shape here, right? But it also has to do with how does one molecule of water interact with another molecule of water and all the other molecules of water around it? What do they see when they see each other? How do they interact together? Because that action on aggregate is what gives us some of our physical properties, chemical properties that we are so interested in. And this is why understanding molecular polarity is so important, right? Because if I have a polar molecule, right, so it's got a delta minus on this side and delta plus on the other side, and he sees another molecule that is also polar, that has little partial minuses and partial positives, how do you think they're going to interact with one another? Does that polarity change anything about the way they see each other? Yeah, Sarah says that opposites attract. So because now I have these little charges, those charges are actually going to attract one another. They'll be like sticky, right? The H's are going to attract the O's, and the O's are going to attract the H's, and you have a big network of these little attractive forces, right? As we saw when we did ionic compounds, they kind of lined up really nicely to make these crystal structural shapes. These ones in the solid phase do the same thing. If you have strong intermolecular forces, they will also line up to make nice crystal shapes because they're maximizing those positive, negative, attractive forces. If you compare that to a bin that has a nonpolar substance in it, right? Let's say instead I've got this bin that just is full of CH4s, and CH4s obviously the CH bond is not polar, so we have no polarity, no bond molecular polarity here. How is one CH4 molecule going to interact with another CH4 molecule? Are they going to be as attracted to each other as these guys? Yeah, as Erica says, they won't really be attracted to one another. There's no partial positives to be attracted to partial negatives. There's no positives or negatives there at all. There's no reason for these two to want to see each other as they're kind of trying to interact with each other, right? As opposed to this, you can hopefully clearly see, oh yeah, that positive is going to attract that negative, okay? So this is the basis for what we call intermolecular forces, right? And, oh, I better go to, and intermolecular forces are, as the name describes it, right? The forces that individual molecules feel when they interact with other molecules. So inter is in between. So forces between molecules those forces are going to depend on the properties of the individual molecules themselves, whether they are polar or nonpolar, okay? There are 4 different types of intermolecular forces that I want you to know. And I'm going to put them in this chart, and we're going to list them from strongest at the top down to weakest at the bottom. So depending on the type of compound, we get different kinds of intermolecular forces. And then we'll get some examples here. And we'll see, again, that the physical and chemical properties of my substance depend on the intermolecular forces that they have, okay? So here we go. So starting at the top, in terms of forces between individual atoms, ions, or molecules, the ionic type compound has the strongest intermolecular forces. If we looked at it as a molecule, it's not really, it's an interparticle force because they're not really molecules, because they have ion-ion attractive forces. And that is, like, as for instance, this positive charge attracts the negative charge, right? So examples would be something like sodium chloride or MgOH magnesium hydroxide, right? Because those are ionic type compounds. And this, hopefully you could understand the positive ion attracting the negative ion, because there's a whole charge there, that is going to be stronger than the attraction between the partial positive and the partial negative between these 2 individual molecules. Okay, so that's ionic. Now for covalent compounds, we actually have several different kinds of covalent compounds, right? Our covalent compounds can be nonpolar or they can be polar. And actually, we actually have 2 special cases of polar compounds. We're going to split this up. We have like regular polar and special polar. Special polar happens when you have hydrogen attached directly to an F, an O, or an N specifically. Put this in quotes, special. Okay. It gets its own special category because it's really strong as compared to regular. Part of the strength of that, of these has to do with the relative size of the atoms, and then the fact that these also have lone pairs that are going to attract. So that gives us a different, we give it its own category of intermolecular forces. So if I have this special thing here where I have an H directly attached to an F, O, and N, I call this hydrogen bonding. And I'm apologizing right now. I didn't come up with this name, and I never would have called it that, because it gives you the mistaken idea that if you have a hydrogen bonding to something in your molecule, like with a covalent bond, then it must do hydrogen bonding. And that's totally not true. Hydrogen bonding is an intermolecular force that only applies if you have a hydrogen bonding to one of these atoms, fluorine, oxygen, or nitrogen. But when that does happen, you have this intermolecular force called hydrogen bonding, which is really strong and important, especially for us, because we are water-based life forms, and water is subject to hydrogen bonding intermolecular forces because you have a hydrogen directly attached to an oxygen, and it's a polar molecule. But you would see the same thing in ammonia, NH3, and in hydrofluoric acid as well. Okay. Regular polar, we're just going to call that a dipole interaction. That's one dipole, that means 2 poles, right? Something that's polar that has 2 poles interacting with something else that's polar that has 2 poles. So anything else that is polar, if it doesn't have hydrogen bonding, then it's just dipole-dipole. So HCl, as opposed to HF, HCl would be dipole-dipole, right? Or like the SO2 example that we showed earlier. Let's see, what else did we see here? So all of these, N, O, and F, these would be hydrogen bonding. But then over here, there's our SO2. That would be dipole-dipole. This CH2F2 is dipole-dipole because, again, the hydrogens aren't attached to the fluorine itself, right? Hopefully you see that. So that would be dipole-dipole. Okay. And then if you are nonpolar, we're going to call this London dispersion forces. After the guy who discovered it was something London. Sometimes you also hear these called van der Waals forces. Sometimes you'll also hear these called induced dipole. For the purposes of this class, I'm just going to call them London dispersion forces or dispersion forces. So anything that's nonpolar entirely, like CH4, as we saw, or if you have polar bonds but they cancel out, as in the case of CO2 and SO3, those all, because they are nonpolar molecules, they get to be called London dispersion forces. That's the kind of forces that apply to them. So here, then this is kind of a flow chart, like a sideways flow chart, for you to determine what kind of intermolecular forces something must be subject to. If you could determine if it's ionic versus covalent, and then if it's covalent, if you can determine if it's polar or nonpolar, and if it's polar, if you can look for H attached to FO or N, then you can determine what kind of intermolecular forces that molecule might be subject to. Does that make sense in theory? Okay, so let's just practice a little bit of this. Yeah, oh, dipole, yeah, so dipole is just if I'm polar, if I'm a polar molecule, but I don't have this H attached to FO or N, right? So as Zachary says, how do you distinguish this from that? As you're going through here, if you determine that it's polar, like this one, then say, does it have an H attached to FO or N? And if it doesn't, then it's just dipole-dipole. Here's one way to remember it. I might have put this in the lecture notes. This is just silly, but hydrogen bonding is fun. All right, so let's look at this one from your worksheet here. I'm just going to put this down here. Tell what kind of intermolecular forces the following compounds are subject to. All right, so help me out with this one. LII, what kind of intermolecular forces do you think it's subject to? Good, Nicole has got it, right? Li is lithium. That's a metal, it's in group 1. So that automatically tells you this is an ionic compound and it's subject to ion-ion intermolecular forces. And that's pretty easy, that's nice, nice to do. Okay, what about F2? Dispersion, all right? So fluorine with fluorine, two nonmetals that have to be covalent. And you can draw it out and so on and so forth. But since it's bound to itself, any difference in electronegativity is zero. It's going to be nonpolar. So that's got to be London dispersion forces. That's what it's subject to. Good. What about NaCN? Good. Ion-ion. Sodium is in ion. CN is a polyatomic ion. So that's an ionic type compound. Good. What about HCN? Great, Erica and Nicole have it. You both said that it was dipole. Now, hopefully you didn't just eyeball that. You don't have to eyeball it, especially on the test. You don't have to eyeball it. Some of these you can eyeball, and by eyeball I mean you just look at it and you can deduce, right? Oh, sodium's a metal, so that's ion-ion, right? But once you get to the point where there could be a polar bond and you're not sure if it cancels out, then you probably ought to go through the steps of drawing your Lewis dot structure and then determining if it is polar or nonpolar. So, all right, here's your Lewis dot structure. You've got a triple bond between the carbon and the nitrogen, single bond between the carbon and hydrogen. carbon and hydrogen bond is not polar, but the carbon and nitrogen bond is ever so slightly polar. It's a difference of 0.5. So there's going to be a partial positive on the carbon, partial negative on the nitrogen. It'll pass the line test. So this has dipole-dipole interactions because it is like regular polar. Put that in parentheses. Nobody calls these special polar and regular polar. They just say polar with FO and N and polar without. But they're both polar. Okay. What about HCl? Good, dipole-dipole. A little easier to see if it's just two atoms, right? Then the bond polarity is the molecular polarity because the bond is the molecule. Okay, what about CO2? Good, but if you don't just know that, you'll want to draw it out. When you draw the Lewis dot structure, you'll find that it's got two double bonds, so it's linear. So even though the individual bonds are polar, they cancel out. So the whole thing overall is not polar. And so this is going to be London dispersion. This is where eyeballing it's going to get you into trouble, right? You might be like, oh yeah, the CO bond is polar. It's definitely a polar molecule. But if they cancel, then it's dispersion. You have to watch for that. Good. Okay, what about CO? Dipole, yeah. Good. C4H10. Oh, do I have to write that whole thing out? What do you guys think about that? Sarah says nonpolar. Did you have to write it out, Sarah? Sarah says, no, I don't have to write it out to determine that it's nonpolar. Because why? Yes, Sarah has it. If you can determine that there's no polar bonds, then it's not polar, right? So you have two options for being nonpolar. Either you have nonpolar bonds or you have polar bonds and they cancel. Here we had polar bonds and they cancel. Here we don't even have polar bonds. The difference between C and H is 0.4, so there's not going to be any polar bonds in there. Well done. Okay, what about H2O? Hydrogen bonding. Yeah, we've seen it before. All right, and SO2? So again, could eyeball it, but we probably ought to be, especially on a test, be slow and careful. There's a lone pair there that pushes those oxygens down, and the SO bond is polar. So the actual shape of it is like this. And so you get, it passes the line test there. So it is dipole-dipole. Really, if we're getting any of these wrong, the problem is that we're not carefully going through the steps that we did here to determine overall molecular polarity, right? If we don't go slow and steady and take our time, then we might miss it. Or if we forgot how to identify an ionic compound, that'll cause us problems too, right? If you were confused by these two because you forgot that the sodium and the lithium were ions, then that's something to pay attention to. Okay, any questions on this section? Okay, all right. So we've got an extra column here we never filled out. What are the properties of these things that arise from having these kind of intermolecular forces? That's the next question. Well, the stronger the forces that are binding the pieces together, then that's going to give us some interesting properties. So for instance, for ionic compounds, we find that they tend to have very high melting and boiling points, okay? Because in order to go from, if you'll remember, all the way back to like our first day where we were talking, if you look at the solid, where our individual particles are crammed together and stuck in space, right? Versus a liquid, where our individual particles are still really close together, but they can kind of slide past one another. Versus a gas, where our individual particles are really far apart, right? and not touching each other at all. You can see how if you're really attracted to one another, it's going to be harder to break up these pieces that are stuck together, right? And have them flow past, right? It's hard to move past something that you're attracted to. And so to go from solids to a liquid, which is what it takes to melt, that's going to take a lot of energy. And to go from a liquid to a gas, where you have severed all connections to other things around you, that's going to be even harder, right? So very high melting and boiling points as compared to these ones here. Our hydrogen bonding have relative, for other covalent compounds, they're high melting and boiling points. These are moderate melting points, boiling points, and these are relatively low melting points and boiling points, okay? Because again, we said if I've got a couple molecules of CH4, there's nothing keeping them together, right? So if they're crammed together, there's not a barrier to start moving past one another, really. And to get them to separate completely, they're like, whatever, that's fine, that's easy to do, right? So like as, for instance, I can give you an example. Sodium chloride, if you want to melt that, the melting point is something like 800 degrees Celsius, right? You couldn't, your ovens are not hot enough to get there, right? Water, as our poster child for hydrogen bonding, has a melting point of what? What's the melting point of water? 32. 32? Erica. You're right, it's 32 Fahrenheit. What is that in Celsius? Okay, we're good. 0 Celsius. Just so that we're comparing apples to apples, right? So if we have 800 Celsius with sodium chloride, 0 Celsius for water. Let's see, what's the melting point? Let's look up SO2. All right, melting point is negative 72 degrees Celsius. Okay, perfect. Oh, Chase had it. Perfect. Okay, what about CH4? What's the melting point of CH4? Nice, yeah, negative 182 degrees Celsius. Okay, this is exciting, guys. We've done a lot of theory saying here's how things bond and here's how they connect and here's what their shapes are and here's what their polarity are. And you're kind of like, I don't care about it. I'm like, what does this even mean? Well, this is practical, right? Now I can see, this is something that I can see, I can measure with the thermometer, hypothetically, right? But I can see the difference between each of these is a pretty small molecule, right? These are not huge molecules, and yet they have such different melting points, and that's based entirely on the structure of the individual pieces inside of it, right? You can say, oh yes, well these are ions, they're very attracted to one another. That's why you can't get it to just melt, right? And this one has hydrogen bonding, so that makes it, insofar as all of your covalent compounds, it's going to have a much higher melting point than something which is just dipole-dipole. You can see how there's really a significant difference between what I call the special polar category of hydrogen bonding and this quote-unquote regular polar category of dipole-dipole. And then, of course, the London dispersion is like, I mean, it's at room temperature, it's already gas, and it's been a gas forever, right? Because even the boiling point of CH4 is quite low, right? Let's see, look that up. Oh yeah, the boiling point is negative 161. Right, so before the SO2 will even melt, the CH4 has boiled 100 degrees beforehand because it was just not attracted to each other at all, really. Okay, Sarah's got a great question. Do we need to memorize this table? And the answer is yes, absolutely you do. You do not need to memorize these details right here, right? This is just illustrative details. But understanding the intermolecular forces that arise from different types of compounds and being able to identify, if I give you a molecule, what kind of intermolecular forces it's subject to, and being able to compare properties, that's important. In fact, there's more properties. I should continue with this. So we've got high melting points, high boiling points. As a solid, they tend to be crystalline because they're maximizing the positive, negative charge interactions. It's the same thing here. As a solid, these tend to be crystalline. Like crystalline water or solid water makes ice crystals, which we don't think that is crystalline, but if you zoom in on that shape, I think you would notice that it is. Certainly when you see snowflakes, they do appear to be crystalline. Sugar is a covalent compound which has lots of OHs on it, and it also makes a crystalline solid, as you see there. As opposed to down here as a solid, these ones have an amorphous shape. So think wax. Wax is a good example of a solid, which is London dispersion force. You have to get a molecule that is very, very large in order to even be solid, because the rest of them have already just evaporated by the time they get down. So there's another property that you'll want to be aware of. Additionally, you'll see things like solubility. This is important. All of these, the ion-ion and the dipole-dipole and the hydrogen bonding, all of these are going to be soluble in water, hypothetically. But these ones are not. They're soluble only in nonpolar solvents. So I think this is like oil and vinegar, right? So vinegar would be a molecule which has hydrogen bonding, so it'll be soluble in water. Vinegar is a solution that contains water and acetic acid. Whereas oil is a nonpolar solvent, so it's only going to be soluble in other nonpolar solvents. If I try to put them together, I can shake it up and get them to mix for like a minute, and then they're going to separate out. And the reason is that the water molecules are just more attracted to each other because they have those little partial pluses and minuses than the oil molecules, which don't have the little pluses and minuses. Does that make sense? There is a bit of memorization for this test, Sarah. You're not wrong. But hopefully I've been trying to teach it in a way that you can kind of see the logical progression of like why we get here, right? So I don't want you to just memorize like, oh yes, ionic compounds have very high melting points and boiling points. So much as I want you to understand that like because they have stronger intermolecular forces, it's going to keep those pieces together longer. Chase has a really good question. Would alcohol be London dispersion? Because that's why it doesn't fully mix with water. Oh, that is such a good question, Chase. Okay, so alcohol and water. In terms of organic chemistry, alcohol is a generic term for a functional group which has an OH on it. Okay, so hang on a second. So I could have a molecule with one carbon, so carbon-based compounds are organic compounds, one carbon, and if I have an OH on that one carbon, that would be an alcohol. And if I have two carbons, hang on, here's another carbon. I don't want to get too derailed, but this is such a good question. I can't prevent myself from answering it. If I have two carbons with an OH at the end, that is also an alcohol. So because it contains this alcohol functional group, I can say this is an alcohol type molecule. Does that make sense? Okay. And then if I have, see what I do here. If I've got three carbons, then it's still an alcohol. And if I have three carbons and I like swap places here, what if I say, let's stick this up here, move this in, so I can kind of change how they're connected. It's still an alcohol, right? So there's a couple different alcohols here. You can, of course, make a molecule that's got 4 carbons and 5 carbons and 6 carbons, and so on and so forth. So this one's got 3 carbons. There we've got 4 carbons. Okay, So all of these are alcohols. Now, as you might guess, we get kind of an interesting thing that happens when we have a molecule like this. And you say, okay, this part is doing hydrogen bonding. And that means that it's really polar. It's going to interact really nicely with other OHs. It's going to interact really nicely with water. And then we have this part of the molecule, which only has London dispersion forces, right? Only has nonpolar bonds. So it's not going to interact very well with water. And then you might say, okay, well, then what does this do, right? Is it soluble? Is it not soluble? And the answer is it depends on how many of each you have, right? So the smaller molecules that has a ratio of fewer carbons to oxygens, they interact very well with water. So this is completely miscible with water. That means that it's soluble in all proportions. So this is methanol. You can have 99% methanol, 1% water, works well, 1% methanol, 99% water, works well, soluble in all proportions. That's wood alcohol. You wouldn't want to drink that. It could make you go blind if it didn't kill you. Next, we have 2 carbons. This is ethanol. This is the one that people drink. All forms of alcohol are poisonous, including this one. Just usually this one makes you pass out before it kills you. And again, it's soluble in water at all proportions. This top one is propanol. And this bottom one is isopropanol, just like you buy at the grocery store, isopropyl alcohol. Both of those soluble in all proportions. Now we get up to 4-butanol, and it's pretty soluble, but not entirely soluble. So you could put some of this in water, but if you put too much, then it will separate. And then pentanol, which gives 1 more carbon, it's too much, and it's just not really very soluble at all. And so the more carbons you get, the less soluble it becomes. But the small molecules tend to be soluble, and that's important for a number of things that we cover in a lot more detail in Chemistry 1120. But let me give you just one other example, just to see, how this applies. In organic chemistry, we'll often use these line structures to represent large organic molecules. Okay, and each of these points is a carbon, right? So, for instance, if you look at the molecules that make up your lipid bilayer, they look something like this. Then oxygen, carbon, oxygen, carbon, oxygen, phosphorus, oxygen, oxygen, negative charge, oxygen, carbon, nitrogen, carbon, positive charge. Okay, so this is phosphatidylcholine, one of the principal components of your lipid bilayer. And hopefully you see it is these intermolecular forces that we have just been talking about that give the lipid bilayer, that gives this molecule the properties that makes it self-assemble into a lipid bilayer. Okay, you have here literally 36 carbons, right? Nonpolar, definitely London dispersion forces, right? Okay, and then over here you have positive and negative charges. This isn't like my OH where it's like I have hydrogen bonding. No, I have ion attractive forces going on up here, right? And that gives this molecule this properties of being like this end really wants to be soluble in water, and this end really doesn't want to be soluble in water. And that's, I know in biology, they just kind of shorten this to be like, here's a polar head, and these are nonpolar tails, and they're going to self-assemble like this, and you're just going to draw the polar head with the nonpolar tails. And this is how your lipid bilayer self-assembles, so that your polar head or ionic head is on the inside of your cell, which has an aqueous cytoplasm, and on the outside of the cell, which has also an aqueous environment, right? There's your vascular environment. And on the inside of this lipid bilayer, you have these long nonpolar tails. Does that make sense? Okay, I think it's cool. I'm sorry, this is a little bit beyond what we cover in this class, but this is like why you care about it. Okay. And and if anything I can inspire you to care about what we're talking about, I'm like, I want to inspire you to care about what we're talking about because it's so cool, right? It's so cool to understand what is going on in the world around us. Like, why does that even happen? Right? I think it's cool. Okay, so here we go. So you need to know this chart and you do need to understand the general properties of it. In fact, that's the next thing in your covalent properties worksheet is to arrange groups of compounds by boiling point. So let's look at this briefly because we still have a little bit more to go today. Okay, so arrange the groups of compound by boiling point from lowest to highest. Now there's something else I haven't told you here, but maybe you guys can guess. Here, each of these is subject to dispersion forces. How am I supposed to compare if they're all the same? What do you think? Like which would have a higher boiling point? Yeah, Sarah says look for the number of atoms, right? Because the larger number of atoms means it's a larger molecule. There's a larger surface area over which these intermolecular forces can act. They kind of get tangled up in each other if they're really big. So you just say, all right, this molecule has 5 atoms. This molecule has 14 atoms. So, right, like this one being smaller is going to have a lower boiling point. Does that make sense? So if I just compare these, I would say, okay, well, the lowest is going to be the CH4 because it's the smallest. And then next is going to be C2H6 because it's the next smallest. And then having 3 carbons makes it that much bigger. And then having 4 carbons makes it that much bigger. That's basically what you're going to do. If all else is the same, if your intermolecular forces are the same, then you can compare based on size. But if they're not, then you have to, intermolecular forces is a much stronger effect. So here, comparing these guys, we already know what CH4 and CH2H6 are because we did it here, right? Both of these are limited dispersion because they're going to be this, so they're going to be the smallest. Okay, so then let's look at these two. Which of these two, the H2O or the HO, CH2, CH2OH, which of those is going to have the higher boiling point? Right, so we like H2O because it has hydrogen bonding, right? We're like, that's great. But you also have to watch out because this one also has hydrogen bonding, right? So we can look at HOH as having 2 hydrogen bonds, right? There's an OH there and there's an OH there. And this one also has 2 hydrogen bonds. There's an OH here and there's an OH there. And then it has some extra space in between. So that makes it bigger, right? It's a larger size molecule with the same number of hydrogen bonds there. So that actually gives it the higher boiling point. Does that make sense? So H2O is the smaller of the molecules that has 2 hydrogen bonds. And then this is actually ethylene glycol. So water has a boiling point of about 100 degrees Celsius. Ethylene glycol is about 190 degrees Celsius. Okay, so that's that section. Okay, we are going to add to this chart just a little bit. I'm going to expand on it. This chart currently shows you how things interact in these type of compounds that we've spent a lot of time discussing, right, in this class. So we spent a whole chapter on ionic compounds, now a whole chapter on covalent compounds. And here, since we're kind of comparing properties of substances that we can see, we're going to add in a couple of different types of molecules that we're not going to spend more time on, but we're just going to kind of, for comparison purposes, that you should know, okay? So there's a table in your lecture, no, there's a table in your textbook. That's what it's called, a textbook. there's a table in your textbook that goes over this, and I've replicated it a little bit in your worksheet that you're just going to kind of fill in, and it's based on this. So there's two other solid types I want you guys to know. I'm going to add them right here. So solid type number 1, a covalent network solid. So this isn't just, this is types of solids. If I'm a solid, covalent network solid is actually held together by covalent bonds. This is different from covalent molecules, where the individual molecules are held together by these intermolecular forces. Okay. Instead, we're going to say here, we've got individual atoms and it's just covalent bonds in all directions. Okay. So as an example from your lecture notes, okay, so that's looking at water in the solid state, where you have individual water molecules that might be attracted to each other with this dotted line. That's the hydrogen bonding intermolecular force. And hopefully you see, in order to do this, they pop open these, they make these rings, they pop open. And that's why water expands as it freezes, is it's trying to make space to maximize those intermolecular forces. Also note that's 6-sided. That's why snowflakes have 6 sides. Isn't it cool? It's cool. Okay. And here's your ionic compound, which is just held together with the ion attractive forces in all directions. This is your, I'm just going to do a Google image search for this really quick. So here is a covalent network solid, or a model of it, basically, where essentially, instead of having dotted lines connecting these atoms, as in this is an attractive force, you have solid covalent bonds attracting the atoms in all directions. So it's a little bit like this, except that instead of attractive forces, it's a covalent bond, and the covalent bond is much stronger than the attractive force, right? And so as a result, because it's so much stronger, your properties are going to be extremely high melting points, boiling points, okay? And of course, crystalline as well. Also not soluble in water because it doesn't have the positive and negative charges, individual pieces like the ion does. Also tends to be very hard, not brittle. That is to compare it to ionic compounds, which are brittle. In the ionic compound, it's possible to misalign the positives and the negatives. If you tap on one edge, it'll misalign, and then your positives being attracted to the positives will repel one another. So it will fall apart. It's pretty brittle. But the covalent network is not brittle because you don't have that possibility of misalignment. And it's very hard. Just what does it sound like I'm describing? A substance that's really hard, but that's a crystal and has a really high melting point. What does that sound like? You guys think of anything? Eric has got it. That is a diamond. Diamond is a classic example of a covalent network solid. Also graphite is another example of a covalent network solid. Okay, yes, exactly, just like a diamond. Perfect. So that's one type of solid. Additionally, oh, and now I've got to move my diamond out of the way. All right, last thing I'm going to put down here is a metal. A metal is a solid that doesn't really fit nicely into this ionic or covalent category, right? Like, so if you have a gold ring, or if you have a silver spoon, or if you have a chrome bumper, right? These are metals that are solids. And it's held together, we call it the electron C model. And this is, as metals, they have low electron affinity, low ionization energy. So their electrons kind of go out to play. And it doesn't, the atoms don't really care which electrons belong to whom, right? So you might have these nucleus, 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 and the electrons just kind of like live in a sea of electrons, and they flow, right? So as a result, if you push electrons in one end, you can get electrons out the other end, no problem, right? That's where we get the property of conducting electricity. Conducts electricity. And we also get the property that it's malleable and ductile as opposed to being brittle, right? You can hammer this, you can draw it out into the line. They're like, whatever, we don't really have a structure here like you've got in these other ones, right? Shiny, because that's your electrons are reflecting light when they come in. So good examples of these, just like gold or silver as elemental ones, brass, bronze as alloys. Anything that's a metal has this other model. Does that make sense to you guys? Okay, so on an exam, I could name a type of compound or molecule and say, what would the properties, physical properties of this be? You could have to select them. Or I could say, here, look, let me name these properties. Can you tell me what kind of compound that would be? Does that make sense? Would those be fair questions? Okay. And then again, in your worksheet, your covalent properties worksheet, and I'm just going to drag it over here. It's you have this chart. That's exactly what we just did. So you can fill that in. Anyways, I'll let you go. Have a good weekend.